Picture a flooded street that used to flood once a decade. Picture a winter storm that feels wrong. Now imagine Earth as a snow globe with a hairline fracture you can't see unless the light hits just right. Here's the question we're auditing today. Is climate change a smooth dial we can turn back, or a set of hidden switches we might flip only once? I'm Rowan K. Mercer, and this is the Science Audit. I want to begin on the human scale, where this story actually lives, in your commute, your grocery bill, your grandparents' memories of normal winters, your kids' future definition of summer. We tend to treat climate like background music, always there, usually predictable, sometimes dramatic. But Earth isn't a static backdrop. It's a living system of flows, heat, water, carbon, salt, ice. And living systems don't always change smoothly. Sometimes they hold steady, until they don't. If you've ever walked across a frozen lake, you know the feeling. Most of the surface looks solid. The danger isn't obvious from afar. It's hidden in thickness, temperature, weak spots, and stress. Climate tipping points feel like that, not constant chaos, but the possibility that under the surface, stability is thinning. So let's name the core question cleanly. Is Earth warming like a dimmer switch? Every bit of CO2 adds a proportional bit of change. Or are there thresholds where the system reorganizes itself, and the new state keeps going even if we stop pushing? That second possibility is what people mean by tipping points, and it's why the topic triggers both fascination and dread. And it's also why our brains struggle with it. The human mind is a linear machine. We're built for cause then effect, more effort then more result, more heat then more melt. But Earth often behaves nonlinearly. Nonlinear doesn't mean random. It means the relationship curves. It means you can push gently for a long time and see little change, then push the same amount again, and suddenly everything accelerates. Here's a metaphor that will carry us through the entire audit. Imagine a ball resting in a valley. The valley is a stable climate state. A nudge rolls the ball up the slope, but gravity brings it back. That's stability. Now imagine the valley itself slowly changing shape, because the landscape is made of feedback loops. The sides get less steep. The ridge to the neighboring valley gets lower. At some point, a nudge that used to be harmless becomes enough to cross the ridge. And once the ball rolls down the other side, it doesn't come back on its own. That's a tipping point. Before we get lost in drama, we need rules. The Science Audit runs on definitions, evidence, and honest uncertainty. So today, something qualifies as a tipping point only if it has three features. First, a threshold. A boundary in conditions, often temperature, where behavior changes qualitatively. Second, self-amplifying feedback. Not just warming causes melt, but melt causes changes that cause more melt. The kind of loop that pulls you forward. Third, persistence. The system doesn't snap back quickly when the forcing stops. It either becomes very hard to reverse, or it stays altered for centuries or longer. What doesn't qualify? Simple trends. A steady increase in heat waves is serious, but it's not automatically a tipping point. A coral reef bleaching event is devastating, but whether it's a tipping point depends on whether recovery becomes impossible due to self-reinforcing loss. We're going to be precise, because precision is how you respect a scary topic without turning it into a campfire story. Also, uncertainty isn't weakness. In science, uncertainty is a measured thing, like error bars on a ruler. Pretending we know more than we do is not bravery, it's negligence. But pretending uncertainty means nothing to worry about is another kind of negligence. Our job is to locate the ridgelines, even if we can't yet map every pebble. So what are the big candidates, systems with enough evidence that we can actually audit them? Tonight, we're going to walk through 4 ice sheets, ocean circulation, the carbon cycle on land, and the ocean's role as a heat and carbon sponge. And then we'll talk about the part that makes this truly unsettling, cascades, how one switch might shove another. Let's start with the core physics intuition, feedback loops. If you remember only one thing from this entire video, let it be this: stability is often the victory of negative feedback over positive feedback. Negative feedback is a stabilizer. Think thermostat. The room warms, the heater shuts off. The room cools, the heater turns on. The system resists change. It wants to return to a set point. Positive feedback is an amplifier. Think microphone squeal. A tiny sound goes into the mic, the speaker plays it louder, the mic hears the speaker, it gets louder again, and suddenly the whole room screams. The system doesn't resist change, it multiplies it. Earth has both, constantly fighting. Clouds can cool by reflecting sunlight, but they can also warm by trapping heat. Vegetation can pull CO2 from the air, but heat and drought can kill forests and release carbon. Ice reflects sunlight, but melt exposes darker surfaces that absorb more heat. So here's a question you should keep asking as we go. In each system, are stabilizers still strong, or are amplifiers starting to dominate? Because that's the difference between a dial and a switch. Let's audit ice sheets first, Greenland and West Antarctica. Not sea ice, the floating stuff that melts and affects ecosystems and weather, but grounded ice sheets, kilometers-thick reservoirs of frozen water sitting on land. If they lose mass, sea level rises. That's the human-scale consequence. But the tipping logic is about the physics of how they hold together. Start with a simple loop, albedo. Albedo is Earth's reflectivity, how much sunlight gets bounced back to space. Snow and ice are bright. They reflect a lot. Dark ocean and bare rock absorb more. So when ice melts, Earth gets darker. Darker Earth absorbs more solar energy. More energy means more melt. That is a classic positive feedback loop. Melt begets warmth begets melt. But that alone isn't enough to prove a tipping point, because the melt could still slow down if temperatures stabilize. The deeper question is whether parts of these ice sheets have geometric and mechanical instabilities, structures where retreat causes conditions that make further retreat easier, even without additional warming. For Greenland, picture an enormous frozen dome. The edges spill ice toward the sea through fast-moving channels called outlet glaciers. Think of them as the ice sheet's arteries. Warming air increases surface melting. Some meltwater drains through cracks to the base, lubricating the interface between ice and bedrock. It's like placing a thin layer of water under a heavy box. Suddenly it slides. Now add the ocean. Many Greenland glaciers terminate in fjords. Warm water can undercut the glacier front, thinning it, making it more likely to break off, calving, so the glacier retreats inland. As it retreats into deeper basins, the ice face can become taller, exposing more area to melting and fracturing. Is there a specific temperature threshold where Greenland's long-term loss becomes self-sustaining? That's one of our key uncertainties. But we can still say something precise. There is a difference between realized melt and committed melt. Realized melt is what you see now, ice lost in this decade. Committed melt is what the system is locked into over centuries because of the state it has entered. A metaphor: if you push a boulder to the edge of a cliff, it might sit there for a moment. The fall hasn't happened yet. But the commitment has. Gravity has a claim on the future. Greenland's commitment could be triggered at a certain sustained warming, often discussed in the range of a couple degrees Celsius above pre-industrial, with wide uncertainty depending on models and processes. The key point isn't the exact number, it's that the ice sheet can have inertia in time, but not necessarily in fate. Now West Antarctica. This is where the geometry turns eerie. Much of the West Antarctic ice sheet sits on bedrock below sea level. That means the ice is grounded on a floor that slopes downward as you go inland, like a bowl. And the boundary where grounded ice transitions to floating ice shelf is called the grounding line. Here's the instability. If the grounding line retreats into deeper water, the ice at that line becomes thicker, and thicker ice flows faster outward under its own weight. Faster flow thins the ice upstream, which can cause further grounding line retreat. That loop, retreat into deeper water causing faster flow causing more retreat, is called marine ice sheet instability. You don't have to love the jargon. Think of it like this: if the doorway out of a crowded stadium gets wider the more people leave, the flow accelerates on its own. The system's exit becomes self-opening. Then there's the ice shelf itself, the floating buttress. Ice shelves act like braces. They don't raise sea level when they melt because they're already floating, but they slow the discharge of grounded ice behind them. If warm ocean water thins the shelf from below, it weakens the brace. The glaciers behind it can speed up. Some researchers have also proposed a mechanism called marine ice cliff instability. If retreat exposes very tall ice cliffs, they may collapse under their own weight, potentially accelerating loss. This idea is actively debated. Some models produce dramatic outcomes, but the real-world physics of fracturing and failure is uncertain. In this audit, that goes in the plausible but contested bin. Here's a micro-question that matters more than it sounds: how fast is fast? When people hear ice sheet, they imagine geologic time, millennia. But in climate risk, fast can mean within a human lifetime. Even if full collapse takes centuries, the moment of commitment, the crossing of the ridge, could happen in decades. And sea level doesn't need a complete collapse to reshape coastlines. So how do we know ice sheets are changing now, beyond photos and headlines? We watch Earth with instruments that feel like science fiction. GRACE satellites, Gravity Recovery and Climate Experiment, measure tiny changes in Earth's gravity field. Not gravity, in the abstract, but the literal tug of mass beneath them. When an ice sheet loses billions of tons, the gravitational signature changes. It's like weighing Greenland from space. Altimetry satellites measure surface height, how the ice surface rises or falls. GPS stations measure how the land rebounds as ice mass is removed. Multiple tools cross-checking each other, because this is exactly where you want redundancy. Here's the next system, the ocean circulation, specifically the Atlantic Meridional Overturning Circulation, the AMOC. If you've heard it called the ocean conveyor belt, that's a useful mental image, as long as you don't imagine a simple machine. It's more like a global breathing pattern. Warm, salty surface water flows northward in the Atlantic, releasing heat to the atmosphere, helping keep parts of Europe milder than their latitude suggests. As that water cools, it becomes denser and sinks in the North Atlantic, flowing back southward at depth. This overturning helps distribute heat, influences sea level along coasts, and nudges rainfall patterns across the tropics. Now, what drives sinking? Density. And density is controlled by temperature and salinity. Cold and salty water sinks. Warm and fresh water resists sinking. So here's the vulnerability. If Greenland melts and dumps fresh water into the North Atlantic, the surface becomes fresher. Fresher means less dense. Less dense means less sinking. Less sinking can weaken the overturning circulation. That's a pathway to a circulation shift. What would be the feedback? If the AMOC weakens, it can change regional temperatures and rainfall, which can influence ice melt and atmospheric patterns, potentially feeding back into the system. But we have to be careful. The AMOC is naturally variable. It wiggles over years and decades. Distinguishing a long-term weakening trend from natural fluctuation is a difficult statistical problem, not a political one. Still, multiple lines of evidence suggest the AMOC has weakened compared to earlier periods, and paleoclimate records show it can shift abruptly under certain conditions. Paleoclimate is Earth's memory. Ice cores capture ancient atmospheres in trapped bubbles. Ocean sediments preserve chemical proxies that hint at past currents and temperatures. It's like reading the diary of a planet that didn't know we'd someday ask it questions. In that diary, we find episodes where Atlantic circulation changed sharply, associated with abrupt climate shifts in the North Atlantic region. That doesn't prove the same will happen tomorrow, but it does prove the system is capable of nonlinearity. Now, the carbon cycle. This is where the plot becomes deeply personal, because carbon is the currency of life, and the exhaust of our civilization. Think of CO2 as heat-trapping insulation in the atmosphere. Not a blanket in the sense of warm and cozy, but in the sense of slowing the escape of infrared radiation to space. Earth absorbs energy from the sun, and it must radiate energy back out. If you change the atmosphere's ability to let that heat escape, you change the planet's energy balance. But the atmosphere doesn't hold all the carbon. The land and ocean are huge reservoirs. For decades, they have buffered our emissions, absorbing a significant fraction of what we release. The ocean absorbs CO2, forming carbonic acid and changing chemistry, ocean acidification. The ocean also absorbs heat. More than 90% of the excess heat from global warming goes into the oceans. That is both a gift and a threat. It slows atmospheric warming in the short term, but it loads the ocean with energy that can return in the form of marine heat waves, altered currents, and ice shelf melting from below. On land, forests and soils store carbon. But warming and drying can stress ecosystems. Trees die. Fires increase. Pests expand their range. When forests burn or decay, stored carbon returns to the atmosphere. That can turn a carbon sink into a carbon source, a potentially self-amplifying loop. Then there's permafrost, ground that stays frozen for at least 2 consecutive years, often for thousands. Permafrost is like a freezer that has been quietly storing ancient organic matter, dead plants and animals since the last ice age. When it thaws, microbes wake up and begin decomposing that organic matter, releasing CO2 and methane. Methane is especially potent in the short term. It's like a heat trap that burns bright and fast compared to CO2's long, persistent glow. If permafrost thaw accelerates, it's a feedback, Warming thaws permafrost. Thaw releases greenhouse gases. Greenhouse gases cause more warming. Peatlands, waterlogged soils rich in carbon, can also flip from storing carbon to releasing it if they dry, burn, or degrade. These are not sci-fi hazards. They are measurable processes happening now, with uncertainties about how far they can scale. So here's a question that should make you sit up. If the planet's natural buffers weaken, does each additional ton of human CO2 become more dangerous than the last? That's the logic of compounding risk. At this point, you might be thinking, okay, we have candidates. But how close are we to any threshold? How would we even know? This is where we step to the edge of understanding and do the stress test. How do you detect a system approaching a tipping point? In many complex systems, ecosystems, markets, even the human body, there are early warning signals. One is rising variance. The system's fluctuations get bigger. It wobbles more widely around its normal. Another is slowing recovery. If you perturb the system, it takes longer to return. Imagine nudging the ball in the valley. The walls have become less steep, so it rolls back more slowly. A third is flickering. The system briefly jumps between states, like the ball occasionally hopping over the ridge and then returning, until eventually it doesn't return. These patterns show up in mathematics and in data, but detecting them in the real climate system is brutally hard. Why? 4 reasons. 1. Limited analogs. We have good instrumental measurements for about a century, and high-quality satellite data for a few decades. Some tipping processes unfold over longer spans. 2. Sparse observations. The ocean is huge. The Antarctic is harsh. We don't have sensors everywhere we'd like. 3. Models have structural uncertainty. A climate model isn't one equation, it's millions of lines of approximations of fluid dynamics, chemistry, biology, ice physics. If a crucial process is misrepresented, like how meltwater finds its way through an ice sheet, your threshold estimates can shift. 4. Interacting subsystems. Earth isn't a row of dominoes laid out neatly. It's more like a spider web, pull one strand, tensions redistribute everywhere. Now, let's audit the key mysteries, system by system, with intellectual honesty. I'm going to mark them in plain language, strongly supported, uncertain, or under active debate. Greenland first. Strongly supported. Greenland is losing ice mass, and warming increases melt. We have satellite gravity, altimetry, and field measurements. Strongly supported. Albedo feedback exists, and meltwater affects ice dynamics. Uncertain. The precise temperature threshold for long-term self-sustaining loss. Some studies suggest that sustained warming beyond a certain range could commit Greenland to major loss over centuries. But the number depends on model assumptions and on how quickly we could cool again, if we ever did. Here's the key insight: commitment is not the same as catastrophe tomorrow. But commitment is still a form of irreversible choice. So ask yourself, if you were piloting a ship and you saw that the channel ahead narrows into rocks 2 miles out, would you say, "We haven't hit anything yet, so it's fine"? Or would you turn now while turning is still easy? West Antarctica next. Strongly supported. Warm ocean water is intruding beneath some ice shelves, thinning them. Strongly supported. Certain grounding lines are retreating, and geometry matters for stability. Strongly supported. Marine ice sheet instability is grounded in physics and supported by multiple modeling studies. Uncertain. The timescale and the extent. Which basins are most vulnerable? How quickly can retreat proceed? How do local bedrock features and frictions slow or accelerate it? Under active debate, the magnitude of ice cliff failure, processes, and whether they could drive extremely rapid collapse. This is where headlines can outrun evidence. The responsible stance is neither dismissal nor panic, it's sustained monitoring and targeted research. Now the AMOC. Strongly supported. The AMOC matters for climate patterns and can shift. Paleoclimate tells us it has changed abruptly in Earth's past under certain forcings. Uncertain. How close we are to any threshold today. Observations suggest weakening, but the record is short, and direct measurements of the AMOC at key latitudes are relatively recent. Some studies infer long-term weakening using sea surface temperature patterns and other proxies. Others caution those proxies can be influenced by different processes. So what would abrupt actually look like in practice? Not Hollywood instant ice age. More like a rapid shift over years to decades in circulation strength that reshapes regional sea level along the U.S. East Coast, alters storm tracks, and moves rainfall belts, especially in the tropics where billions depend on seasonal rains. If that sounds distant, make it human. Rainfall belts determine agriculture. Agriculture determines food prices. Food prices influence stability. Climate isn't just weather, it's the operating system of civilization. Now, carbon cycle feedbacks. Strongly supported, permafrost is thawing in many regions, and warming increases the potential for greenhouse gas release. Strongly supported, forests are experiencing stress from heat, drought, and fire, and disturbances can turn ecosystems into net emitters. Uncertain, the size and timing of these feedbacks. Permafrost carbon release is likely to be significant, but it may unfold more as a long, persistent source than an abrupt switch, though abrupt thaw processes, like thermokarst collapse, can locally accelerate release. Peatlands and forests have thresholds, but the system is heterogeneous. It depends on region, management, and compounding stressors. Now comes the part that changes the emotional temperature of the room: cascades. Because Earth's biggest risks may not live in any single system. They may live in the connections. Here's a simplified cascade story, and I want you to feel how it could happen without any one piece being doomsday on its own. Warming increases Greenland melt. Meltwater freshens the North Atlantic. Freshening reduces sinking, weakening the AMOC. A weaker AMOC shifts rainfall patterns, potentially drying some regions and stressing forests. Forest stress increases fires and dieback, releasing more carbon. More carbon increases warming. Warming increases melt. That's not a prediction. That's a plausible network of couplings. The question isn't, will this exact chain happen? The question is, how many couplings exist, and how strong are they becoming? When complex systems fail, it often isn't because one bolt snapped. It's because redundancy eroded until a normal stress became fatal. Earth has redundancy. But we are applying a global stress, greenhouse gases, fast enough to test those redundancies. And this is where I want to pull in the contrast from the outline, the holiday vibe, the deceptive calm. You can stand on a ridge at night and see beautiful lights in a valley, towns, homes, streets. Everything looks stable, organized, safe. But a ridge is a boundary. A few steps can put you in a completely different watershed, where every drop of water flows to another ocean. Climate boundaries can look like that. You may not feel the line under your feet. The air may even feel normal. But the system can be migrating toward a divide. So let's do an honesty segment, the part that determines whether this video is science or theater. What do scientists broadly agree on? What's contested? And what would falsify extreme claims? Agreement: Earth is warming due to human greenhouse gas emissions. The physics of radiative forcing is solid. We measure it in satellites and at the surface. Agreement: ice is losing mass. Sea level is rising. Heat content of the ocean is increasing. Extremes are changing. Agreement: the climate system contains positive feedbacks and thresholds. We have evidence from theory, observations, and paleoclimate. Contested: the precise tipping thresholds, the timescales, and the probability distribution. For many systems, we can say, risk increases with warming, but pinning down, at 1.7 degrees Celsius this happens by 2073, is not honest. What would falsify extreme claims? If someone claims, the AMOC will collapse within 5 years, a falsification would be sustained observations showing stable overturning strength outside predicted bounds. If someone claims, ice sheets can't contribute significant sea level rise for centuries, falsification would be accelerated discharge and grounding line retreat beyond their modeled constraints. In science, bold claims must expose themselves to sharp tests. That's how we keep off from becoming superstition. Now, there's another subtlety: timescales. People use tipping point to mean sudden disaster, but in Earth systems, the tipping can be sudden while the full consequences unfold slowly. Imagine snapping a small twig on a tree. The snap is instant. But the tree doesn't fall right away. It weakens, becomes vulnerable, fails later in a storm. Commitment can be that snap. Sea level rise can be the slow fall. So what does this mean for reality, your reality, my reality, the choices we make and the way we narrate the future? Here's the philosophical takeaway: we live inside a coupled system with hidden thresholds. Stability is not guaranteed. It is maintained by balancing loops we rarely think about. The reason normal exists is that countless processes, ice reflectivity, ocean circulation, plant uptake, atmospheric dynamics, are constantly doing work to keep Earth in a habitable range. We grew up in a particular valley in that stability landscape. Our agriculture, our cities, our infrastructure, even our cultural rhythms are adapted to that valley. The question is not whether Earth will remain habitable in some abstract sense. Earth has been many things. The question is whether it will remain stable in the specific way that our civilization quietly depends on. Ethically, this becomes a problem of risk management under deep uncertainty. You don't need perfect certainty to avoid catastrophic thresholds. You wear a seatbelt not because you're certain you'll crash today, but because the downside is huge and the cost is low. You buy insurance not because you love fear, but because you respect asymmetric risk. Tipping points are asymmetric risks. If you cross a ridge, you may not be able to push the ball back. That changes what prudence means. Now, agency. We need to reframe it. The question isn't, can we control Earth? That's a fantasy, and it always was. The question is, can we keep our pressure within the range that preserves the valley we evolved in? That means two things at once: reducing the forcing, emissions, and increasing our ability to observe and respond, monitoring an adaptation that assumes nonlinearity. Let's make that practical. If you want to know whether the planet is nearing certain thresholds, what should we watch? For ice sheets, grounding lines, the location and rate of retreat, ice shelf thickness, ocean temperature at the continental shelf. These are like stress fractures in a bridge. You don't ignore them because the bridge still stands. For the ocean circulation, sustained AMOC indices derived from moorings, temperature salinity profiles, and sea level patterns. ARGO floats, thousands of drifting sensors, profile temperature and salinity through the upper ocean. They are like a distributed nervous system for the sea. For carbon feedbacks, methane fluxes in permafrost regions, soil temperature and moisture, fire frequency and intensity, forest health metrics, and the net carbon balance of ecosystems. And for the global picture, Earth's energy imbalance, the difference between incoming solar energy and outgoing infrared radiation, and ocean heat content. Because at the deepest level, climate change is an accounting problem, energy in versus energy out. Now I want you to sit with a hard truth that is also, strangely, empowering. Emissions trajectories change tipping risk. This isn't binary. We're doomed or we're fine. Risk is a curve. Every tenth of a degree matters. It matters because it changes how many subsystems are stressed at once, and how close the ball creeps toward the ridge. And adaptation planning must consider nonlinearity. If you assume smooth change, you build for the average trend. If you accept the possibility of thresholds, you build for resilience, flexibility, buffers, response capacity. You stop designing your civilization as if the climate is a stable backdrop. Let's return to that snow globe image. In your mind, hold a glass globe with a tiny Earth inside. You can shake it: storms, floods, heat waves. The flakes swirl. Then it settles and looks calm again. That's the psychological trap. Calmness after turbulence feels like recovery. But imagine there's a fracture in the glass. Each shake widens it, not visibly at first. Calm doesn't mean whole. Now zoom out one more level. The camera pulls back and you realize the snow globe is in a hand. A human hand. Not a villain's hand. Not a hero's hand. Just ours. That's the real revelation. We are not outside the system holding it like an object. We are part of the system applying the pressure. So here's the synthesis, what we've learned on this journey. First, tipping points are real in principle, and some exist in Earth's past and present dynamics. They require thresholds, self-amplifying feedbacks, and persistence. Second, the strongest audited candidates with serious evidence and physical grounding include parts of the major ice sheets, especially West Antarctica's vulnerable geometry, and potentially aspects of ocean circulation and carbon cycle feedbacks. The exact thresholds and timelines vary, and some mechanisms are contested. Third, the deepest risk may lie in cascades, interacting subsystems that reduce Earth's stabilizing capacity, turning gradual pressure into abrupt shifts. Now the contemplative takeaway, a thought experiment I want you to carry into your own life. Imagine you're walking at night and you come to a bridge. There's no obvious damage, but you're told that under certain loads, the bridge can enter a vibration mode that amplifies itself, each oscillation feeding the next, until failure. Engineers call it resonance. You don't need to see the collapse to respect the condition for collapse. So ask yourself, in your own decisions, your community, your vote, your work, your conversations, do you treat Earth like a bridge with a safe load limit? Or do you treat it like an infinite structure that will forgive any strain because it has always been there? And now the next great question, the one that opens the next door. If climate stability is not a guarantee but a maintained balance, what other, background certainties, in our lives are actually dynamic systems, quietly held steady until they aren't. And if time is the ledger where consequences get paid, what does that say about the promises we make to people we will never meet? If you want the evidence map, what is strongly supported, what's uncertain, and what's under active debate, stay in this session and watch the next video that's appearing on your end screen. It's designed to deepen this audit without repeating it. And if you want more audits like this, subscribe, not for drama, but for a consistent framework, definitions, mechanisms, measurements, and honest uncertainty. One question for you, and it's easy to answer. Which possibility unsettles you more, an abrupt switch we don't see coming, or a slow commitment we only notice when it's too late? Drop your answer in the comments, and tell me what part of the system you most want us to audit next.